Hey, you're here for AP Chemistry with Mrs. Mays, and today we're looking at acid-base equilibrium. We're going to start by talking about the pH scale. Here's some pH levels of common substances you may encounter in everyday life, like battery acid in your car battery. That one looks kind of scary. Don't touch it. Lemon juice is very acidic. Gastric fluid means the stuff inside your stomach that's digesting your food. Then there's other things like ammonia that you might use to clean your windows or mop your floors, baking soda that you use in making pancakes, or bleach that you might use to clean your house. Those substances all have a known pH, and we describe things as acidic or basic depending on their pH level. In neutral solutions, the concentration of hydrogen ions and hydroxide ions are equal to one another. That's what makes them neutral. So in water, the hydrogen ion is equal to the hydroxide ion concentration, and they're both in water equal to 1 × 10⁻⁷ molar. And of course that's pure water. For other solutions, when the hydrogen ions increase, then that means the hydroxide must decrease, and vice versa. So the product, when we multiply hydrogen ions times hydroxide ions, is always going to be 1 × 10⁻14 molar, every single time. In an acidic solution, we mean that the hydrogen ions are outnumbering the hydroxide ions. There's more protons in the solution than hydroxide ions, and that's what makes it acidic. The opposite is true for a basic solution. Hydroxide would then outnumber hydrogen ion. So we have the pH scale to help us describe how much hydrogen ions are present. The kW describes the ion product constant for water. That's just the product of multiplying the concentration of hydrogen ions times the hydroxide ion concentration. pH stands for power of hydrogen, and by power I don't mean superpower like how strong it is, but rather what is the actual exponent as a power of 10. That's what P stands for. It's the negative log, which is the opposite of 10 that's raised to the power. 10 to the x is called the anti-log, because those operations are inverse of one another. So the pH would be less than 7 for an acidic substance. That means the concentration of hydrogen ions is greater than 1 × 10⁻⁷. In a basic solution, I have a pH that is less than 7, so the hydrogen ion concentration is not equal to, but rather less than 1 × 10⁻⁷. pH simply means take the negative log of the concentration of hydrogen ions. And by looking at the pH, you can tell if something is acidic or basic. Here's the hydrogen ion concentration, and the pH simply means we're looking at what is this exponent here. So when the pH is 0, that means you have 10 raised to the power of 0. 3 means it's 10 to the power of -3. So whatever this exponent is here, take the sign off of it, or change the sign, and that becomes your pH. For basic solutions, we would look at the concentration of hydroxide. So we have something called the pOH to measure hydroxide ion concentrations. So when we're working with acid and base, we're going to need to know how to change pH to pOH. So if we have hydrogen ion concentration equal to 1 × 10⁻⁷ molar, what we mean is the pH would be the negative log of that concentration. So we simply, in our calculators, take the negative log of 1 × 10⁻⁷. And you can do this with your calculator. I'll do it just for fun, just to show you how it works. So we take the negative log of 1 × 10⁻⁷, and you'll see that we could have done this in our head. It's 7. Remember I said pH means take that power and get the negative sign off of there, so the pH is 7 when the hydrogen ion concentration is 10 to the minus 7. It's really that easy. But what if it doesn't completely dissociate? What if it's not that easy to do the math? Well, we'll use our calculator then, it's no big deal. So where we have acetic acid that's 1 molar, but it only dissociates about 5%, then we would say the concentration of hydrogen ions will be about 5% of 1 molar, or 0.05 molar. Now we take the pH, or the negative log of 0.05. All right, calculator time. So we do the negative log of 0.05. I get a pH of 1.3, which makes sense for acetic acid. That basically means that we have a substance that is acidic, and since it says acid, that seems reasonable. Suppose we have a weak acid that dissociates only 8.1%. So just because it says that it's a weak acid does not mean that the pH is closer to 7. That just means it doesn't completely dissociate into ions. You can have weak acids that are just as destructive as any strong acid out there. Now the pOH measures the power of hydroxide. So again, we're looking at the exponent in our times 10 to the whatever power. That's where the power is coming from, not like, hey, how strong is that? It's the power, mathematically speaking. So pOH describes the concentration of hydroxide, and sometimes it's more convenient to express our pOH than pH, especially if hydroxide is the thing in our solution. So when the pOH is equal to 7, it's a neutral substance. When it's less than 7, this solution is basic because the concentration of hydroxide ions is greater than 1 times 10 to the minus 7. In an acidic solution, the pOH is greater than 7. And to find the pOH, we simply take the negative log of the hydroxide ion concentration. So it's the same process as what we used with pH, only now we're dealing with the hydroxide ions. One simple tool to remember is that the pH and the pOH will always add up to a total of 14. Kw is equal to the product of hydrogen ions times hydroxide ions. So when we multiply those, we'll always get 1 times 10 to the negative 14. And the negative log of Kw equals the negative log of hydrogen times hydroxide. And because we're multiplying with logs, that means the negative log of hydrogen ions plus the negative log of hydroxide ions. So the negative log of Kw is called pKw, and that's where we get the pH plus the pOH being equal to 14, because Kw is 10 to the minus 14, so if I take the negative log of that, I get 14. So let's complete this chart to make sure we are solid on converting pH to pOH to the concentrations. So first, if I have a pH of 7, I have a pOH of 7, but that means my pH is also 7. Hydrogen ions then have a concentration of 1 times 10 to the minus 7 molar, and hydroxide also is 1 times 10 to the minus 7 molar. So this one is neither acidic nor basic. The pH says this one is neutral. But where the pH is 10, that means I have a base. So let's find the pOH. I do 14 minus 10, so the pOH is equal to 4. Hydrogen ion concentration will be 1 times 10 to the minus 10 molar, and the hydroxide ion concentration is 1 times 10 to the negative 4 molar, which is more than 10 to the minus 10, and that's why our substance is basic. Now we're going to have to work a little bit harder because 2.3 is not quite as easy to work out in my head as a 7 or a 10. having that decimal there kind of makes me work a little bit harder, just a little bit. So 14 minus 2.3, that's going to be 12 minus, okay, so 11.7. And now I need to do 10 raised to the negative 2.3 power to figure out my hydrogen ion concentration. So let's get a calculator and figure out what that is. So I do the antilog, 10x to the minus 2.3 power, and that is 0.005. Or 5 times 10 to the minus 3, right? So the hydroxide ion concentration we would calculate in a similar way, 10 raised to the negative 11.7. I take my POH and I put it as my power of 10. Don't forget to change the sign or you won't get the right answer. So the concentration of hydroxide ions is 10. So antilog raised to the negative 11.7 power. So we'll call that 2 times 10 to the minus 12. And look at the pH. Is this acidic or basic? Since the pH is less than 7, we know that this one is an acid. Now let's start from pOH. If pOH is 14.5, the pOH is 4.5, so I subtract 14 minus 4.5 to get my pH. 8.5? No, 9.5. Subtracting numbers. So then I find my hydrogen ion concentration by doing 10 raised to the negative 9.5 power. So antilog, and then negative 9.5. 3.2 times 10 to the minus 10. We would do something similar for the hydroxide ion concentration. So 10 raised to the negative 4.5 power. Use the antilog, negative 4.5. 3.2 times 10 to the minus 5. Okay, you know how to run the calculators. I'm only going to show you to do this 2 more times. Let's look at the pH. Let's see, 9.5 is greater than 7, so this substance is a base. For the next one, I have 3.4 times 10 to the negative 5 is my hydrogen ion concentration. So to calculate the pH, I take the negative log of the hydrogen ion concentration. 3.4 times 10 to the negative 5. So, calculator time. I do negative log, then 3.4, scientific notation, negative 5. That gives me a 4.468. Let's round that to say 4.5, shall we? So that pH is 4.5, and my, oops, wrong box. In my last example, the 4.5 was my pOH, so I know I just switched these two. So I would expect these two to be about switched. Let's see what happens. I should get something times 10 to the minus 10 here, right? So I take my 10 raised to the power of 9.5, but I'm not going to just use 9.5. Remember, we rounded that. So I'll use whatever's in my calculator with all of the digits, the non-rounded number. Alright, back to what I had before. So first I do 14 minus the answer I had before. So 9.5 is about what we estimated, and then I take my antilog raised to the negative answer And finally, I get my hydroxide ion concentration, 2.94, we'll call that 2.9, raised to the power, or times 10 to the power of minus 10. So now you see why I wanted to keep all of my sig figs, because it looked like a very similar problem to what we had before, but it was slightly off because this concentration is slightly more. So that means my hydroxide ion concentration is slightly less than what this was before. Alright, check out your pH value and decide, is it acidic or basic. Right, this one is an acid. Okay, one more. We're going from hydroxide ion concentration to filling out all of the chart. So let me get my pOH first by taking the negative log of the hydroxide ion concentration. We just start with what we're given, right, and work from there. So the negative log of 4.6 times 10 to the minus 9. That gives me 8.3. So pOH is 8.3. Now I want to do 14 minus the pOH over here to get my pH. And while I'm at it, I'll do the concentration too. So 14 minus that answer that I had, that has helps me to not have to type everything in. So 5.7 is my pH, and let's do the concentration of hydrogen ions will be the antilog of that negative answer. So we'll call that 2.2 times 10 to the minus 6. So, and 2.2 times 10 to the minus 6 is the hydrogen ion concentration. Since my pH is less than 7, this is indeed an acid. So you have an assignment in your packet to work through concentrations and pH and pOH just to make sure that we're solid in how one relates to the other. Make sure you do both pages, because some of the ones on the second page of the assignment are trickier than the first page. Great, we'll see you in class.